Lesson 26, activities. We're going to find dy dx for this particular function. In this case, it's actually not hard to solve for y, and then you can just do your normal derivative calculation. But that particular derivative would involve taking the derivative of a big square root. So you'd have a chain rule. Technically, when you solve for y and take the square root of both sides, you'd have to do plus or minus. And it's actually just much simpler to do this the way that I want us to do it, which is to do implicit differentiation, because the x's and y's are all kind of mixed together. And it's not just a y equals, which is what most of our equations this semester have looked like. So we'll take a derivative of both sides of that equation. The derivative of the left-hand side, x, is just 1, equals the derivative of y squared plus 1 is 2y times dy dx. I will go ahead and put the plus, the derivative of 1 is obviously 0. And then we're going to solve this thing for dy dx. I didn't ask us to do this in the demo problem, but I will ask us here. It's not hard. You just divide both sides by 2y. And so that's our answer. The derivative of dy dx, in this case, for this curve is just 1 over 2y. If you want to, you could compare that to the old way of doing this one, which would be to solve this equation for y, right? And then when you take the square root, you got to put in a plus or minus. So you could take the derivative of those two functions, one for the plus and one for the minus, and you'll get there. It's not going to look like 1 over 2y, but it'll be equivalent. But for sure, it is not nearly as clean as what we just did. So implicit differentiation not only allows you to differentiate a new class of equations, but also sometimes gives you cleaner solutions than the old technique. Okay, we're going to take a derivative of both sides here, but we're not going to bother getting dy dx by itself. So sine of stuff becomes cosine of the stuff times the derivative of the stuff. Derivative of x over y has to be a quotient rule. I'll square the bottom. Bottom times derivative of the top minus the top times derivative of the bottom. But the derivative of the bottom isn't just plain 1. The derivative of y is 1. dy dx. Remember, anytime you're taking a derivative of something with a y in it, you do your normal derivative rule, and then you multiply by dy dx. That's the left-hand side. Now we also take the derivative of the right-hand side. ln of stuff becomes 1 over the stuff times the derivative of the stuff. The derivative of 3y to the 5th is normal, 15y to the 4th. But because it's y and not x, at the end, after you've completely finished your derivative rule, you multiply by dy dx. So the derivative rule in this case was chain rule applied to the ln. And so that was 1 over stuff times the derivative of the stuff. And that ended at the 15y to the 4, and then times dy dx. Now, again, technically we could do algebra to get the dy dx by itself. In this case, there's 2 of them. That makes it a little bit more complicated. But the idea here is that you're going to get all of the terms with dy dx onto one side and every term without dy dx onto the other side, and then factor out dy dx. Not going to go through all the steps, but I will say you would multiply both sides by this y squared. You could distribute this cosine of x over y into both of these terms up here. You would then have, and also, yeah, and I think that's it. You could clean up this side. We got y's that cancel, and then these y squareds are going to come over here. So it's not going to be so bad on this side. And then you're going to have a single dy dx term on the left and a single one on the right. You're going to bring this dy dx term over by adding the correct thing. And then, like I said, you'll have dy dx's, both dy dx terms on this side with, like an addition sign in between them. And you'll factor out dy dx and then divide by the appropriate thing. You can do it for practice. If I ask you to do one of those, it won't be as complicated as that one up above. Okay, so what we're after here is finding dy dx. That means we do have to solve for dy dx. So let's take a derivative of both sides here. 9x squared becomes 18x. That's ordinary because it's x. Plus 4y squared becomes plus 8y. That's not ordinary. Because it's y, it needs a times dy dx. Don't forget to take the derivative of the right-hand side. It is no longer 25. It is 0. We're taking derivatives of both sides. Okay, here we do want to solve for dy dx. So we'll subtract the 18x from both sides and then divide both sides by the 8y. And we'll go ahead and just reduce the fraction here. So that's a negative 9x over 4y. So there's dy dx. And we're going to use that to find the equation of this particular curve, the ellipse, at the point -1, 2. So we're looking for the equation of that tangent line right there. And we need to find the slope. We do have a generic slope. dy dx generally is this negative 9x over 4y, but we want the specific slope at our point. So it's a little bit awkward, but there is a way to write the notation here. We're plugging in the point x comma y equals negative 1 comma 2. And when we plug in, it's supposed to be negative 9 times the x, so negative 9 times the negative 1 divided by 4 times the y, 4 times the 2. So altogether that is equal to 9 over 8. And that is the slope of that red tangent line in that picture. Seems reasonable. And then we do our mx plus b calculation. So this rest of it is not calculus at all. So y equals mx plus b. Y equals positive 9 over 8 x plus b. Plug in the negative 1 and 2. And then add 9/8 to both sides. So 9/8 plus 16/8 is 25/8. Okay, so that makes the final equation of our tangent line here. Y equals 9/8 x plus 25/8. 25/8 is a hair over 3. It's 3.125, which makes sense looking at the picture. Y-intercept, sure, a hair over 3. Okay, so that one's good. Next page. All right, so here is a crazy looking shape. It is called an asteroid. And we're going to go ahead and find dy dx. So take a derivative of both sides. X to the 2/3 becomes 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3. But that one is a y, so we treat it differently. After the normal derivative, we multiply by dy dx by the chain rule equals the derivative of 2, that's 0. And again, this one says find dy dx. That means you got to solve for dy dx. So we'll subtract the 2/3 x to the negative 1/3 from both sides. And then we'll divide both sides by 2/3 y to the negative 1/3. So we get negative 2/3 x to the negative 1/3 divided by 2/3 y to the negative 1/3. It's in our, I mean, that's it. That's the derivative. It's in our best interest to simplify this. The 2/3 cancel, so we're just going to get a negative sign. I'm going to write my fraction here with the negative sign in the front. X to the negative 1/3 really means we can put that thing on the bottom and make it x to the positive 1/3. And x to the positive 1/3 really means the cube root of x. And so there's really, and maybe don't write this just yet because I'm going to rewrite it in a second. So it's really the cube root of x on the bottom. Similarly, y to the negative 1/3 downstairs can move up and become y to the positive 1/3, which is a cube root of y up here. And I'm going to erase this and make it actually a single cube root. It's a nice property about radicals, that when you have the quotient of two radicals with the same index, you can make a single radical. So I think that's about as good as it's going to get for the derivative. And then we're going to use that dy dx equation to find the equation of our tangent line at a particular point. That point is, what is it, 1, 1. So we can draw a tangent line. Looks like the slope here maybe is like a perfectly negative 1, maybe. And the y-intercept looks like it's roughly 2. Let's see how it goes. Okay, so we're going to plug in y dx equals, we're going to plug in x and y. In fact, I'm going to not write that part. I'm just going to write 1 comma 1. And this means we're plugging in 1 for x and 1 for y. So negative cube root y over x, 1 over 1. The cube root of 1 is just 1, so negative 1 is the slope. That was what we guessed looking at the red tangent line over there. And now we'll do our mx plus b. So y equals negative x plus b. Plug in the 1 and the 1 here for x and y. And b is equal to 2, which is also what we guessed looking at that red tangent line. So the final equation here, negative x plus 2. It's the equation of that tangent line to that crazy looking shape that's called an asteroid. Notice it's spelled differently than the space asteroid. Space asteroid has an E in it. Asteroid. Okay, elliptic curve has this form. We're going to find dy dx. There's a little historical note you can take a look at if you're interested. Fermat's last theorem is one of the most famous theorems in mathematics. So let's see if we can find dy dx here. So we'll take a derivative of both sides of our equation. So left-hand side first, derivative of y squared is 2y times dy dx equals derivative of x cubed is 3x squared, that's ordinary, plus derivative of ax. A is a constant, so the derivative of ax is just the coefficient, which is a. And then plus b, that b is a constant, so its derivative is nothing. Piece of cake to solve this one for dy dx. Just divide both sides by the 2y. 3x squared plus a over 2y. And that's it. And we have played around with sliders on GeoGebra in a previous demo. And so if you want to take a look at exploring this curve, this would be a good one to try out in GeoGebra. Number 6. I think we're done with that, right? Just find dy dx. Okay, number 6. All right, so this infinity-looking curve is called the Lemniscate of Bernoulli. You might have heard of the famous Bernoulli family. There's a couple of brothers and a father and an uncle. The whole family were geniuses. Okay, so let's go ahead and take a derivative of both sides. We're not going to worry about solving for dy dx, but we will find the equation of a tangent line at the point 2, 1. All right, so let's do our derivative first. So taking a derivative of both sides, starting with the left-hand side, I see 3 times some stuff squared. No problem. That's 3 times the nope, 2 comes down. 6 times the stuff to the first power, right? 2 comes down, multiplies by the 3, and then there's an invisible power of 1, times the derivative of what's in those parentheses. X squared plus y squared, that becomes 2x plus 2y, but that y needs to get attached to a dy dx. Equals derivative on the right-hand side. 25 is a constant multiplier. Even though it's outside of parentheses, we can just copy it down. It stays x squared minus y squared becomes 2x minus 2y, but again, that y needs to have a dy dx attached to it. Okay, so you don't need to solve for dy dx, so you don't need to go any farther algebraically here, but we are looking for the equation of a tangent line at the point 2, 1. So let's draw that tangent line. Here's the point 2, 1. Looks like the tangent line almost looks like it's horizontal. Maybe it's slightly downhill, right? I don't know if that point is exactly the top point, but something like that. So I'm expecting a negative slope, but pretty close to 0, maybe negative a half-ish. And then a y-intercept, it looks like it's, 1.6 or something, but that's just eyeballed. Actually, as I'm looking at it, that looks like it's maybe a little too steep, but we'll just see what happens when we do the calculus. So we're going to plug 2 and 1 into this equation. Every x becomes 2, and every y becomes 1. So here we go. 6 times 2 squared plus 1 squared times 2 plus 2 times 1 times dy dx equals 25. Parentheses 2 times 2 minus 2 times 1 times dy dx. Let's just do some arithmetic to clean this up. In the parentheses here, I see 5 times 4 plus 2 dy dx. Don't combine those, the 4 and the 2 there, equals 25 times 4 minus 2 dy dx, and don't combine those either. Okay, so I guess we're going to have to do some distributing here. So the 6 times 5 is a 30, which I'm going to distribute through the parentheses on the left. So 30 times 4 is 120. What happened? 120. Let's go right here. 120 plus 30 times 2 is 60 dy dx equals, now this 25 multiplies through, distributes. So 100 minus 50 dy dx. Okay, now that the dy dx's are all unpacked, we recognize that there are 2 of them on other opposite sides of the equal sign. And our goal is to get all the dy dx terms on one side and everything without a dy dx on the other side. So what we're going to do is we're going to add 50 dy dx's to both sides. So I'm going to move this guy over to the left-hand side. And we also want to move everything that doesn't have a dy dx over to the right-hand side. So at the same moment, we're going to subtract this 120 from both sides. And so on the left-hand side, 60 dy dx is plus 50 of them, is 110 of them. And that's equal to negative 20. And then just divide both sides by 110. Negative 20 over 110, or simply negative 2 over 11. So that is, I think that's negative, like a point, actually I don't know what that is, 2 11ths. Maybe like a 0.18 repeating. Let's see if I'm wicked smart. 2 divided by 11. Hey now. All right, so 0.18 repeating is the negative, that number is the slope, which I had said we're going to get something slightly downhill, but not very steep at all. So that seems reasonable, and now we just have to do our mx plus b hunting. So we said that the slope is negative 2 11ths. And then we're going to plug in, instead of b, we're going to plug in, instead of x and y, we're plugging in 2 and 1, respectively. So if we plug in 1 for the y and 2 for the x, on the right-hand side, that's a negative 4 11ths. We add that to the other side. 4 11ths plus 11 11ths is 15 11ths. That is our y-intercept. And is that reasonable? So 15 11ths is, like around 1.5. And that's sure looks good as a y-intercept. And so then the final answer for the equation of our tangent line here is y equals negative 2 11ths x plus 15 over 11.